We live in a wireless world where the surging demand for data and connectivity seems to have no limit. But the RF spectrum, the invisible medium of electromagnetic waves which carries all of our wireless communication, is a finite resource, and there is a limit. The amount of data we send wirelessly grows by approximately 50% every year. Now, this doesn't sound like a lot, but all that compound growth adds up. By 2030, the equivalent of all words ever spoken by humans since the dawn of mankind will be transmitted wirelessly 500 times over every month. To ensure we can meet this ever-growing demand, we need to rethink how we manage the RF spectrum. Spectrum use is governed by three factors: time, location, and frequency. Think about how an FM radio tower works. If you had two FM stations in your town on the same radio channel or frequency, you wouldn't be able to clearly hear either station as their signals would interfere with each other. To solve this problem today, we use isolation, either by geographically separating the transmitters or by assigning different frequencies to different transmitters so their signals don't interfere with one another. Now, as we allocate more and more and more and more frequencies for different radios, things start getting really crowded. And what we end up with is a static frequency plan, like this one, where all frequencies have been allocated. These plans are meticulously drawn out by hand, and it can take years for governments to change these rigid frequency assignments to accommodate new uses. This is how we've managed spectrum for the last 100 years, since the dawn of wireless, in fact, an era of isolation. But what happens when a new technology like 5G comes along that demands more spectrum to carry whole new levels of data? The first problem with our current approach is it's too slow to adapt to new technologies. For regulators to change their allocation plans and find room for new technologies like 5G, they have to take spectrum away from one user and give it to another, a process that takes years. The second problem is that our current approach is poorly designed to take advantage of spectrum that is already allocated but not being used. Many of today's radio systems don't transmit all the time or everywhere. So while the plan tells us all the frequencies are allocated at any given time and place, the actual spectrum usage might look something like this, with lots of unused spectrum available but no one allowed to take advantage of it. It's time for a change. We need to fundamentally shift our thinking away from isolation and look towards a new era of spectrum use, an era of autonomy, where radios are smart enough to manage spectrum themselves without the burden of human intervention. DARPA, a proven leader in U.S. technological innovation, is exploring this new frontier with the Spectrum Collaboration Challenge, SC2, a call to action for innovators around the world to address the looming threat of spectrum scarcity using collaborative artificial intelligence. Today's software-defined radios are able to nimbly change the frequency, timing, and waveform characteristics of their wireless transmissions, which, when empowered by artificial intelligence, enables these radios to move freely about the spectrum and share unused channels. But with multiple radios adjusting their behavior moment to moment in an uncoordinated fashion, this scene quickly devolves into bedlam. Or we might say, interference. The challenge for this next generation of radios is not just to be smart, but to be collaborative and continually communicate with one another to coordinate how the spectrum is used moment to moment. Autonomous and collaborative radios in the SC2 competition are using machine learning and artificial intelligence to coordinate their activity, predict behavior, and agilely navigate through the chaos second by second, resulting in stable predictive behavior.